Hello, we are about to finish this chapter. We only have one section left, that's transformed risk measures. We will study several important techniques that are important to actuarial science. I think likely they were developed by people in this field. And we will see how we can utilize these tools to propose different risk measures other than VAR and TVAR, right? Because VAR is quantile. TVAR is essentially the average of many quantiles. But in the last section, we're going to learn something quite different or dramatically different from what we studied in the previous two sections. In this short video, we're going to focus on the first one. It's called the pH transform. pH stands for proportional hazard. So this So here we can see what pH means. So in order to introduce how we can apply this unique transformation to get a risk measure, we start with something we already know. So let's say we have a non-negative risk measure. Okay, this is a little restrictive, but to us it's fun. We use X to denote loss, and the loss is always non-negative. So there is no loss of generality to us. We use S to denote its survival function. We have already proved this very useful result, right? Actually, we know this. We know this will be from D to infinity, the survival function, right? And here you just need to pick D to be 0. Then we come to this special case. We have the expectation of X, okay? So what we can tell from this result is once we know the survival function, we know the expectation. And if you recall from the very earlier on of this section of this chapter, we actually mentioned that expectation is a possible candidate for risk measures. Okay, although it's unlikely to be a good one because you only look at the average. You don't care about whether it's really fluctuating or not, right? But nevertheless, this is a candidate, right? So that idea we're going to use. So in the next definition, we're going to introduce the pH transform. What is pH transform? So we start with a non-negative random variable X, that is the same. We directly apply this, it looks like a power transformation, right? But we, instead of calling it power transformation, we call it proportional hazard, which we will see in the next slide. But anyways, it's very easy to see. Right? So here we require this gamma to be greater than or equal to 1. That is extremely important. Okay, I claim from this transform, I actually get a new random variable. So this X tilde is actually a new random variable. Obviously, it's closely related to X through this relation, right? I claim this is the survival function of X tilde. What is the survival function? As negative infinity is 1, positive infinity is 0, and S is a decreasing function. So for anything that satisfies, well, there is some continuity condition I ignore, okay? If X goes to negative infinity, it should be 1. But here, it's different because we know we have a lower bound, it's 0, so here we change it to S0 is 1. In general, it should be S negative infinity is 1. This is not a contradiction because S is decreasing. So this is, well, weak sense of decreasing. You can stay flat, right? It's not strictly decreasing, but you can say it's decreasing. So you will have an entire flat piece for the entire negative line, and then you will go down. Of course, the shape, how it goes down, may be different. So here, if I draw the graph, it would be, so let's say this is my original, the survival function. So the original survival function of Sx. Now I apply a power function. And because it's 1 over gamma, the power term is actually less than 1. If you have a calculator, you can try. Let's do this. 0.5 to 0.5, meaning I take gamma to be 2. So if you have calculator, you can hit the numbers, and you will get this is about 0.7, which is bigger than 0.5. What it means is if you apply this special power function with power less than 1, you actually do this. You pump up your survival function. So this is my new survival function as x tilde. By the way, I already call it the survival function just because I easily see all my conditions are satisfied, right? Because 0 to any positive power is 0. 1 to any positive power is 1. So this is good, this is good. And if it's decreasing and I apply power, it's still decreasing, right? Because I can differentiate. And because this is positive, so it's still a decreasing function. So everything works well. This is indeed a new survival function. So by this, we get a new survival function. And once we have a survival function, we know there exists a unique random variable corresponding to it, right? Because there's a one-to-one correspondence between a random variable and its survival function and its CDF and its PDF, right? It's unique. So once we define a survival function, we know there exists some new random variable, which we call x tilde, okay? So that's the mathematical part. Now let's do the definition. So what is the risk measure if you apply pH transform? This is the definition. The risk measure of the original risk x is defined as the expectation of the new transformed random variable. So I want to know the risk measure. So it is the risk of x. And I use expectation of x tilde to define. So according to this definition, so what you do is, our objective is to figure out a risk measure for x, but we don't do it directly. Instead, we construct a new random variable through pH transform, and we use the expectation of this new random variable to define the risk measure for x. Then we achieve our ultimate purpose. So there is a little bit route to do, in order to arrive at the risk measure, but I believe the idea is very straightforward, right? And then we apply this definition again. We can write down what would be my risk measure, right? I put here, it's straightforward to verify that this is greater than 0. So the higher the gamma, the more risky the x. Well, if you don't, so let's say the higher the gamma. So let's say 1 over 3. So let me try my calculator to see what is the value of it. 1 divided by 3. So I get 0.79. So this is bigger than 0.5 to 0.5. So what it means is, so if I apply a bigger gamma, so I will have this. Right? Every time when I push up my survival function, I make the risk more dangerous to the company, right? Because on the right-hand side is the dangerous zone. right? The higher I push up my survival function, that means I have more and more probability on the tail part. Tail is the dangerous zone to the insurance company. So when I push up this survival function, I actually make the expectation bigger. So each time I'm going to increase the expectation. So actually here, we already know this is bigger than, or you can put equal because our gamma can be 1. If gamma is 1, you don't do anything, right? So that's the essential idea behind the pH transform. The reason why we call it pH transform is because of this result. The hazard function of the new random variable is proportional to the old one. Okay, to prove it's actually very easy because we just need to differentiate the new survival function. Okay, it's a power form, so power comes out. The original one is reduced by 1, and then by chain rule, I will need to do the differentiation for the inside function. So we know this is negative of PDF. Of course, here for simplicity, I assume it's a continuous random variable, so I have a density. So here assume x is continuous. Okay, then what I have is this. So let me rewrite what is my the pH transform. Right. So what I can do is first I put my PDF down here. Okay, and for this I can write it as 1 over gamma, which means I times by additional survival, I need to divide by it. Right, I can't change the I cannot change the value of it. So I put back what I originally have. So now let's divide this guy. So what I shall see is my new hazard function is defined as the negative of the derivative and divided by itself. Okay, so what I have, it would be negative cancels, so it will be 1 over gamma times, no, we should actually keep because this is negative divided by, right? This is exactly the hazard function of the original random variable. Okay, this explains why we call this transform pH transform. It's the initials for proportional hazard. And from here, you can easily see why I mentioned in the last slide that when we apply pH, we actually push up the survival function and we increase the mean. It's you can also tell from here, because gamma is greater than 1, okay, equal to 1 is the trivial case, means you don't do anything. Right? Means by applying pH transform, the new random variable has smaller hazard rate. Okay? In life science, or not life science, in life contingency, we actually have a name for this. It's called mortality. Okay, you can roughly think mortality as the probability for instantaneous death. What is the likelihood that people at this age will die? Okay, so the higher the mortality, the more likely someone is going to pass away. So if you are able to reduce the mortality, that means you are going to have a longer life expectation. Okay, longer life expectation means the length of your lifetime is bigger, right? So the same idea is here. Hazard means the somehow it's related to your expectation, right? So the smaller the hazard, the bigger the expectation, because X is likely to live longer. Live longer means it will go to the right-hand side of your x-axis. So the values will be bigger. Bigger values will lead to bigger expectation, right? So that's the rationale behind everything. What I finally conclude is, so this is definition of a pH risk measure. This is greater than my original expectation. This is good to insurance company, or if you want, you can put equality. Right? And we know equality takes when we have equality when gamma equals 1. Okay, usually we don't take gamma to be 1 because you don't do anything. Okay, this is good because this is the reality. Right? Insurance company does not charge you the expectation for the premium. They always charge you much more beyond the expected loss. Right? This is what usually people call actuarial fair value. So there's never fair business, of course, in under this context, because insurance companies needs to pay many costs, right? They need to hire employees. They need to buy various equipment. They need to pay rents. They need to anyway. There's a huge operational costs, right? On top of that, they want to make money. Everything comes from the premium. So the premium will be much bigger than this actuarial fair value. And if you apply this risk measure, it's always above the expectation. So sometimes it's a nice thing, right, to think it that way, because we tend to think an insurable risk is more risky than its mean, right? So now let's do some exercise. Then we will close this video. So for exponential distribution, we know the survival function. So I can easily derive my new survival function, which is just the e to negative lambda divided by gamma times x, right? So what I can tell is my new random variable is also exponential distribution with new parameter, right? Meaning my expectation would be the inverse of my parameter, because my gamma is always greater than 1, right? This is my mean of the previous or the original loss, right? So from here, I can conclude this is gamma divided by lambda, right? So what's the next one? Pareto. So here I use beta. That's because usually, we when we call Pareto distribution, we use alpha and the gamma. But here we reserve gamma, not here. We reserve gamma for the pH transform. So I switch to beta. But anyway, the survival function is easy, right? From here, I get the new survival. So alpha divided by gamma. As you can see from here, my new random variable stays as a Pareto distribution. But the first parameter is no longer alpha, it's alpha divided by gamma. The second one is beta, right? So now I know my expectation would be alpha, beta. So it's alpha, beta, then beta divided by the first parameter minus 1. So I can get gamma beta divided by alpha minus gamma. So here I do need to impose some condition because obviously I want this to be well defined, meaning my first parameter here should be greater than 1, right? That is one of the things we assume. Usually we assume it's actually greater than 2 in order to get the values. So in order for the first parameter to be greater than 1, my gamma should be less than alpha. That's why here is positive, everything's positive, so I get a positive mean, and it's very easy to see this is bigger than my original mean, right? So this is EX. So this is my risk measure, right? So of course, example 9 is relatively easy. I may give you something more complicated to work with, but the mathematics boils down to the same, meaning we still need to do the same thing. Sometimes this step may not be like this. Right here, I directly identify the new random variables in the same family. That saves me time to do the integral. Otherwise, I would have to do this. Right? Recall the original definition to calculate the expectation. You might need to do that. So in some cases, maybe in the homework. Okay. Here I close here.